Hello, thank you for inviting me at this conference. It's too bad that we cannot do it in person, but it's very ingenious what we managed to do this way. So what I would like to talk to you about today, it's work that I have been doing with a number of collaborators. And here you see their picture: Matteo Sesia, Eugene Katsevich, Stefan Bates, and Emmanuel Candes. And we have a paper that has been published earlier this year in Nature Communication that contains most of the information that I'll be talking about. So the topic I'll be dealing with is gene mapping for complex traits. What is the typical setting? We have n observation on a phenotype Y and on p-dimensional genotype X. Now, just for having a sense of dimension, P, the number of possible explanatory variables that are genetic variants, is large, 1 million. And it's also nowadays not small, but typically smaller than P, 10,000, in some cases 300,000 or so in large biobank data sets. Now, the goal with this data is to pass it through some statistical method so that we can identify a set S hat that collects all the genetic variants that are important for the phenotype Y. That is, they carry information on the possible value of the phenotype. So S hat represents position in the genome, and the variation in the genome at this position has an impact on the phenotype. As we tackle this problem, we have to remind ourselves that there is a fair amount of dependence between the X's, and that we want to solve this problem in a way that guarantees us replicability in the selections. Really, selecting the right positions in the genome is very important for the type of medical application one has in mind. We want to learn this S hat because we want to develop drugs, so we need to know which biological pathway we need to target with these drugs, so we don't want to make too many mistakes in the selections. Another challenge is that we really want these selections to be meaningful across ethnic groups, so we want them to be robust. The typical analysis for this type of data, it's done at the univariate level. And what I have here is maybe the simplest form of it, but the substance doesn't really matter. So we scan through every single genotypic variant, and we say that a variant Xi is null if its distribution is independent from the one of the phenotype. The way we test this null hypothesis is using a linear model. So we use the phenotype as the outcome variable. We fit a univariate linear model, and we test the hypothesis if the coefficient relative to the variant Xi is equal to 0 or not. We do this one SNP at a time, and to take into account the fact that we are looking at 300,000, a million SNPs, we are going to control the family-wise error rate at a level 0.05 approximately. What one can notice is that this approach definitely doesn't use the modern machine learning models, and this is perhaps a bit surprising to the community of statisticians. Historically, I think this is mainly due to the fact that it has been difficult to provide the guarantees that geneticists are interested in with these standard machine learning models. In particular, remember the replicability and the sort of guarantees of correct selections that they have in mind. Let me give you an example. This is really old data from 2009. It represents a standard way of displaying the results. On the x-axis, you have genomic position. On the y-axis, you have minus log 10 p-values for each of these tests corresponding to different genomic positions. The numbers that you see on the x-axis correspond to the different chromosomes. And you see that you have these long plots of different p-values, and you have in this plot a threshold line at 8 that indicates in this particular study what has been considered significant. And you can see that there are some locations in the genome that lead to very small p-values. And so we have some discoveries there. And the traits here are triglyceride, HDL, and LDL. And this is data from the NFBC cohort. So what are the limitations of this approach? One is that not all the signal is captured. So this plot refers to the data set I have shown you a minute ago, even if we have a larger collection of phenotypes. And what this entire bar represents is the proportion of phenotypic variants that we could explain using genetic information and other covariates like sex and age. What you can see is that the portion of these phenotypic variants explained by the genetic information, which is the one highlighted in red, it's fairly small. And in fact, the other covariants explain much more. This is a general phenomenon that has been labeled as missing heritability, heritability being the portion of the phenotypic variants that should be explainable by genetic information. The solution of the field to this problem has been to increase the sample size. Undoubtedly, increasing the sample size increases our power to detect loci. This data set that I am showing you only had 5,000 individuals. Nowadays, we fairly often have data sets in the 50,000, 100,000 individuals. The other type of solution that the field has adopted is that when the interest is not simply identifying the variants that are important, but trying to come up with a prediction of what the phenotypic value may be, instead of including only the selected SNP, we use models that include many SNPs, sometimes, in fact, the entire collections of SNPs. The properties of these models are, however, rather unclear. And right now, what the field is really concerned with is that the models that have been constructed in this fashion without any selection really do not seem to replicate well across population. Another limitation is that the interpretation of the findings are difficult. So the plot that you see here, it's much more contemporary than the ones that I have shared with you so far. It refers to height, and the data set that has been used to construct it is the UK Biobank. This is a large collection that includes 500,000 individuals approximately, with a very large number of SNPs genotyped. And you can see that when we use height as a trait in this data set, we can get very strong signals for associations. The minus log 10 p-values that you see on the y-axis reach values of 300. Now, there's lots of points here that pass what would be the significant threshold. So very many SNPs that seems to signal some association. What are the different colors here? The different colors represent an interpretation that geneticists do of these different SNPs. What's happening is that there may be even only one causal variant in this region. So there might be only one genetic variation that really influences height. But because there is a strong disequilibrium, a strong dependence between all the SNPs in a neighborhood in the genome, this association signal between the phenotype and the causal SNP really spreads across all the neighboring SNPs. So when we do a univariate test like the one we have described, all of the SNPs in a neighborhood will show up as significant. So in order to interpret how many real findings we have across the genome, geneticists first focused on loci. That is, they might say, well, on this area around megabase 66, there is something going on for height. And then they study the correlation between the different SNPs, trying to understand how many different groups of SNPs are there here that might show some association. And so the colors here corresponds to these differently identified groups. The name that is used currently is that of clumps. And so you might say, oh, there is a clump of green SNP, a clump of purple SNP, a clump of orange SNPs, and they might all carry an independent signal. Really, though, to understand what are the independent signals, after this sort of approximate counting procedure, geneticists, locus by locus, resort to what they call fine mapping, that is multivariate models that are used to disambiguate the roles of different variants. So what I want to propose to you is an alternative approach, where we'll take the same data and we try to get an output that is corresponding to the desire of the geneticist. But instead of using these univariate models, we're going to really leverage the modern machine learning approach. And we can really go wild with what type of approach we use to identify association. And that's why I called black box rather than statistics, to identify the fact that we really have access to a lot of different algorithms that we don't have to necessarily understand very well. For example, we could use a lasso, we could use random forest, we could use neural net. What we're going to output are discoveries that are distinct and coherent. So we're not going to run into the problem of difficulty in interpretation of how many loci are really associated to height, how many different variants are important in a given region. Our discoveries are going to be distinct. They are going to be replicable in the sense that we are going to try to do what the best we can from the statistical point of view to increase their replicability by providing FDR control on our discoveries. And we are not going to do this looking just at one region of the genome, but we're going to do it across the entire genome so that our return set of discoveries has this FDR control and this interpretability genome-wise, and represent a comprehensive description of how the genes can affect our phenotype of interest. There's two ingredients of this slightly different approach that I want to highlight. One is the fact that instead of doing marginal testing, we're going to do what we can call conditional testing. That is, we're going to declare that the SNP xj is null if it is independent from the phenotype Y, conditionally on all the rest of the loci in the genome. So we don't want to we want to avoid this duplication of signals across variants in the same regions due to linkage disequilibrium. And so we want to discover only the SNPs that have something to tell us about the phenotype in addition to the rest of the genome. The other thing that we're doing differently from the standard approach is that instead of trying to control family-wise error rate, we're going to control the false discovery rate. So the expected value of the number of false positive over the number of features selected. This will translate in a power increase, and it's certainly a better error rate for situations like the one we are interested in considering, where our phenotypes are complex. That is, we expect them to be influenced by a very large number of SNPs. How are we going to do this? We are going to leverage a new theory, now not entirely new, it has been around for 5 years or so, called Knockoff theories. Let me just summarize for you at a high level what this approach is trying to do. So what I have here is simulated data on 500 variables, and I have simulated an outcome for these 500 explanatory variables. The outcome is a function of the variable represented with the red dot. The variables that are represented with the pale blue color do not have any influence on the outcome. Then I run on this data set a lasso with a lambda parameter equal to 3. And I obtain a feature importance statistics that is simply the absolute value of the coefficient of the lasso. And what I plot here is the variable in simple order, 1 to 500, and the value of their future importance statistics. Now, we can see that the lasso does a fairly good job in the sense that lots of the red variables, so the variables that are important, have a high value of a future importance statistics. However, some of the red variables have a small value of the feature importance statistics, and it's not clear where I would do a cutoff. What value of the absolute value of beta should I use to separate the variables that are important versus those that are not? For example, if I were to decide that I'm going to include in my model all the variables that have a coefficient different from 0, I would have a false discovery proportion of about 70%. How do we approach this problem? We're going to leverage some dummy variable. Now, dummy variables are not a new idea in statistics. They have been proposed a number of times in this context. And the idea is that, okay, maybe you can augment your problem with a series of dummy variables that you know are not related to your phenotype. And then you monitor when these dummy variables are selected, and you use this as a measure of when you start making mistakes. What I have listed here are some proposals for how to create these dummy variables. And the one we're going to use is a derivative of the last one. Without spending too much time on this, because I want to get to the analysis of genetic data, let me just give you an idea of what is possible. One construction would be to create dummy variables that are Gaussian, that have the same mean and the same variance and the same covariance of the original variables. And this is the result of an experiment on my first simulation data when I have augmented my set of 500 variables with 500 dummy variables generated in this fashion. The dummy variables are these darker, correspond to these darker blue points. And what I've plotted here is a feature importance statistics. You can see that the lasso does a good job recognizing that these are dummy variables and they have nothing to do with the phenotype. Indeed, most of their feature important statistics is equal to 0. However, you can also see that the distribution of these dark blue dummy variables is fundamentally different from the distribution of the pale blue one here. So if I'm going to use this dark one to understand what happens to the blue ones and when to stop, I'm not going to have really a very informative set of controls, because these controls, these dummy variables, are very different from the null variables in my original data set. Another way of constructing dummy variable that many of you will be familiar with is that of permutation. So you take your original data and you permute the phenotype. Again, you create variables that are completely null. Again, the lasso recognizes them as completely null, but we get a distribution that is fundamentally different from the original null variable in our data set. What this construction of Knockoff does is to create dummy variable that give us a distribution that's much closer, in fact, is the same as those as the null variable in our original data set. So what are these special Knockoff dummies? Here we see their basic characteristics. So we have original set of variables, the Knockoff dummy version of those, and the property that has to hold is what we call pairwise exchangeability. So that for any set of variables, if you swap the original with the dummies, you get a vector that has the same distribution. So in this case, I'm swapping variable 2 and variable 3, and you can see what happens here. If I change the original variable 2 and 3 with their knockoff dummies and place the original at the place of the knockoff, I get the same distribution. The other thing that has to be true is that these dummy variables have to be independent of the phenotype conditionally on the axis. These dummy variables are going to do well because what you can show is that when you construct feature important statistics, the feature important statistics of null variables have the same distribution between the feature important statistic of the original null variables and the feature important statistics of the knockoffs. So if a variable is null, this property holds. So they provide a good negative control. Instead, let me explain a little bit why permutation do not provide a good negative control. So say that we have x1, which is an important variable, and x2 is a null variable. However, x1 and x2 are correlated. Now, x2 can act as a proxy for x1. So we expect the correlation between x2 and y to be different from 0. Now, let's say that we construct x1 permute and x2 permute, permuting the row of the data matrix X. then what is going to be true? It's going to be true that the correlation between x1 and x2 is preserved in the correlation of their permuted copies, and the correlation of x1 permute with y is 0, and the correlation of x2 with y permute with y is 0, because I have broken any relationship between the x's and the y. So this is good. I preserve the correlation between the variables, and these variables are definitely null. But what is also happening is the correlation of x2 permute with x1 is 0. So this x2 permute does not capture the fact that x2 gets a lift from x1. So if I'm going to compare the performance of x2 permute as a predictor with x2, I'm going to see that x2 does a much better job, because x2 permute has forgotten the correlation that existed between the fact that the correlation existing between x2 and x1 translates in a correlation between x2 and y. Instead, the knockoffs are constructed such that this correlation is also preserved. So we don't preserve only the correlation between original variables among the corresponding permuted copy, but also the correlations across. So x2 tilde, the knockoff x2, has the same correlation with the original x1 as the original x2 had with x1. So this negative control will mimic the fact that x2 can get a lift from x1. So in order to use these knockoff procedures, we need to do two things. We need to construct these knockoff variables, and then we are going to use them to construct these important statistics and come up with a criteria on how we're going to filter discovery to make to come up with our set of discoveries that they are control set. I'm going to spend a bit of time on knockoff construction because that's an area where we have done specific work for the case of genotypes. I do have a set of slides on how to construct the knockoff filter, but we probably do not have really time to go over them. I have included them just for the sake of completeness in case some of the people that will look at these slides are not really familiar with the knockoff construction yet. So here is a general recipe for the construction of knockoffs, which we call sequential conditional independent pairs. Let's just look at its realization in the case of three variables. So suppose we have three variables, x1, x2, x3, and we want to construct their knockoff. The assumption we are going to make is that we know the joint distribution of the variables. So we're going to assume that we know the joint distribution of x1, x2, and x3. Given this knowledge, we can sample the knockoff for x1 from the conditional distribution of x1 given x2 and x3. We now also can write down a joint law of x1, x2, x3, the original x, and x1 knockoff, which is simply given by the original law multiplied by this conditional density. Now we then have a law on four variables, and we are going to sample x2 tilde from the conditional distribution of x2 given x1 and x2 original variables and the knockoff for x1. Again, once we have done this sampling, we can add this knockoff variable x2 to our collection of variables, and we know the joint law of all of these variables, and we are going to sample x3 knockoff from the conditional distribution of x3 given the original variable x1 and x2 and the knockoffs variable x1 and x2. Now, this is an algorithm that it's constructed. It also interesting because it tells you that variables with the exchangeable distribution that I described do exist, but it might not be typically very practical. However, the good news, it is very practical in the case of Markov chains. So this is a schematic representation of a Markov chain. So we have our, in this case, our the law of the Markov chains. It's our observed variable. Let's see how we're going to construct knockoffs for them. So the first knockoffs has to be sampled from the joint distribution of x1 given the rest. Now, because the rest is a Markov chain, really only x2 is the only important variable that we need to condition on. So you can get a sense that this will simplify a little bit computations. When we go and sample x2 tilde, again, we have to condition on x1 tilde and all the other variables except x2. But again, all the other variables are going to be only x1 and x3 because of the Markov property, and so on. So there is a reduction on the number of conditioning that we have to do, and we can carry this through and sample our knockoffs. Now, remember, at each step, we have to calculate this new joint distribution so that we can evaluate the conditional distribution from which we have to sample the knockoffs. Now, calculating this new joint distribution requires calculating a normalizing factor, and this might be, generally speaking, rather tricky. That's where the difficulty of the general recipe lies in. But again, in the case of Markov chains, we can actually do a recursive update of these normalizing constants so that we don't have really substantial computational cost unless the number of states is very large. Now, why have I talked to you about sampling knockoffs from Markov models? Because genotypes are very often described as starting from hidden Markov models. This is a fairly incomprehensible picture, but it represents one of the algorithms that have become very popular in the literature, and these are sort of old versions of all of these algorithms. There are even more efficient ones that are used routinely in genetics for imputation and phase reconstruction, that is going from the identification of genotypes to reconstructing which alleles reside in the chromosome that every individual has inherited either from the mother or the father. Without going into details, just believe me that these hidden Markov models are very commonly used to model genotypes. And what we discovered is that once we can generate knockoffs for Markov chains, it's also fairly easy to generate knockoff for hidden Markov models. So this is the typical structure of a hidden Markov model. These are our observations, and this is the hidden Markov chain. And what we're going to do to generate knockoffs is that if we start from these observations, we impute the hidden latent variables, then we create knockoffs for these hidden latent variables using the algorithm for the knockoff for the Markov chains. And then given this knockoff of latent variable, we generate knockoff variables using the emission probability of the hidden Markov model we are interested in. When we talk about genotypes, we're really talking about two hidden Markov models, one that describes the alleles that an individual got from the father, and another one that describes the alleles the individual got from the mother, and these two are put together. So we're going to do that in our data sets as well. Now, let me spend just a short amount of time telling you how we are going to use these knockoffs. Again, please refer to the original contributions in order to understand the properties of this method. I just want to recall them here because they are crucial to understand some of the limitations and next steps that we need to do in order to analyze effectively genetic data. So once we have these knockoffs, we are going to augment our explanatory variable matrix with the knockoffs copy of X. And then we are going to use any machine learning method that we think is going to give us the best way of measuring the importance of all of these variables for our phenotypes X, for our phenotypes Y. And we're going to then get this important variable Z's for the original variables and for the knockoffs. These variables are then going to be used to construct what we call knockoff scores. So for each original variable J, we're going to have only one knockoff score, which is a function of the importance variable for the original variable J and for the knockoff copy of that variable J. all of this combination of original variable has to simply satisfy this symmetry condition. And you can think of it, for example, you take the difference between the importance variable for variable j and the importance statistic for the knockoff of variable j. Now, what are these knockoff scores? Let's familiarize with them a little bit. A large wj says that the variable j appears important. A negative wj says that the knockoff of that variable seems to be more important than the original variable. Now, what is crucial is that for variables that are null, the wj's are symmetrically distributed. And in fact, conditionally on the value of the absolute value of w, the sign for null variable j, the signs of wj's are IID coin flips. And we can leverage that to estimate the FDR. So we're going to say what is our candidate selection set. So we want to select variables that have a large W, right? Because a large positive W says the variable seemed more important than its knockoff and it seemed important to core. So this is our set of candidate selections. Then exploiting the fact that for null variables, W's have the same a symmetric distribution. The sign of W's, it's a coin flip conditional on the absolute value of W. We can get an estimate of the null set. And here is how we can do that simple calculations. And ultimately, what we're going to do is to say, we're going to estimate the FDP of every selection using at the denominator the number of candidate selections that are the number of variables with the large W, where T is the threshold that we have in mind, and at the numerator the number of variables that have a knockoff score that is smaller than minus T. So we look at the opposite direction and see how many negative signs with that particular size of W we have seen. So if this is our candidate selection, the candidate selection includes only the plus values. We see that there is one variable that has a W larger than T, but a negative sign. And so that will be our estimate of how many false positive we have in this data set. So this gives us an estimate of the FDP and an estimate of the FDP that works well, so that we can actually control the FDR if we use this criteria to do our selections. Okay, so let's now go back to really the genetic problem. I've hopefully tried to convince you that we know how to construct knockoffs for this genetic data, because we can approximate the distribution of the genotypes with hidden Markov models. This it's a well-accepted and actually a well-proven technique. So now we can construct these knockoffs. We could run the knockoffs through whatever machine learning method we are interested in and use the knockoff filter, which I have just sketched to make the selection. So how well is this going to do? So remember, doing this, we're testing this conditional hypothesis. The whole meat of the knockoffs is that differently from what permutation do, the knockoff for a variable preserve the correlation of that variable with any other variables. And so they allow us to test this conditional hypothesis. We're going to select an xj to be in our model, an xi to be in our model, if and only if this xi looks as not independent from y, conditional on all the other genotypes. So this is very nice because it avoids the apparent large number of discoveries due to linkage disequilibrium. There's no repetition of the signal. However, there are challenges that come with it. Because the dependence between variants is high, the power to detect any of them becomes low. And this is not a problem that is unique of the knockoffs. It's a problem that really exists for any type of model selection approach. But let me show you in the context of knockoff how this becomes the incarnation of the problem in the context of knockoff. So say that we want to create a knockoff for variable xj. To act as a valid control, our xj tilde needs to be as correlated to any other xk as xj is. So let's represent correlation with angles. So we have our original xj and one other variable xk. We need to construct a knockoff variable xj that has the same angle with xk. So one solution is to make xj tilde equal to xj. That certainly satisfies the correlation constraint, but we realize immediately that this will be a solution that gives us zero power, because when we go and check is xj tilde or xj more important for explaining the phenotype, we're going to get that they have exactly the same level of importance and we're never going to select xj. So the intelligent solution is to try to place xj tilde in a way so that it has the same angle with xj, but it's also as far as possible, the same angle with xk, but it's also as far as possible from xj tilde. And that's what Rina Fogel and Candace did in their original paper when they actually do this for a fixed design, but it's something that has to be kept in mind in any type of construction of knockoffs. Now, what happens when we have many correlated predictors? And I'm trying to capture this, making my plots going from 2 variables to 3. So that's not many, but I think it allows us to capture what's going on. So now, again, we want to create a new variable xj tilde that is the knockoff for xj. If the correlation is strong, we can use the same strategy as before, but you can see that the angle from xj to xj tilde is not going to be much larger, okay? We have gone as far as possible from xj, but we're still very close. So if our predictors are highly correlated, this strategy of trying to go as far as possible doesn't buy us much mileage. As I mentioned, it's a problem for any type of multivariate model. You know, those of you that have worked with the Loci will probably be familiar with the fact that sometimes they select one of the correlated predictor arbitrarily. In Bayesian model selection, this results in having posterior probability for all of the different predictors that are lower than they should be, because they can, each of them can act as substitute for each other. In genetics, fine mapping method resolve this problem by refusing to select among highly correlated predictors and returning a set of possible variants. And we're going to use a similar approach. What we're going to do is that instead of trying to make decision at the single variant level, we're going to define group hypothesis that corresponds to set of variables. And this set of variables are a set of adjacent variables, adjacent position in the genomes. And our group hypotheses are going to be of the type, we're going to say that a group is null if it's independent from the phenotype, conditioning on all the variables in the other group. And you can extend the exchangeability property for the single variable to this group setting. And let me just graphically describe what this means. So we have this group of x1, x2, highly correlated variable. We have to create a knockoff copy of them. And instead of trying to keep the correct, instead of creating a knockoff copy of x1 only, which we know is going to force us to put x1 tilde over here, very close to the original x1, we're going to create a knockoff copy for the entire group of x1 and x2. And this entire group will need to keep the correlation with X3, but can move together. So our knockoff copy of X1 and X2 can be placed over here. And you see that the within correlation is maintained, and the correlation of this group with X3 is maintained, but we do not maintain the correlation across the variables in this particular group. So this group knockoffs, where the exchangeability holds only for across groups rather than within groups, allows us to move these correlated variables together and move them farther apart from their originals. Once we have these groups, of course, we also have to define a group feature importance, and you have many choices for that. In the following, what we're going to do is to simply, in the data analysis that I'm going to show you, what we're going to do is simply sum up the beta coefficients estimated by the lasso in absolute value across all the variables in a group. Okay, so we are going to use this to analyze genetic data. The issue with genetic data is that this genotype variable that corresponds to different locations across the genome are highly correlated locally. This is because of how we inherit our DNA from our parents. Every time that there is a meiosis, there is somewhat of a patchwork done of the parental chromosomes to create a gamete. And this patchwork happens so that portion of the genome that are close tend to be inherited together. So this translates at the level of genotypes in correlation between the XJs, correlations that are local. So what we're going to do is that we are going to use the squared empirical correlation as a similarity measure between the SNPs, and then partition the collection of SNPs by agency constraint hierarchical clustering. So we do a hierarchical clustering, but for variable to be put in the same clusters, they actually have to be adjacent one to the other. And then we're going to cut the dendrogram at different heights, each leading to a different resolution of groups. So what you have here, it's actually a portion of one chromosome, and the shaded blue to white are the groups of SNPs corresponding to cutting the dendrogram at the level indicated by this broken line. At the top here, you have single SNPs with distance with each other represented by the correlation. We are going to then have, depending on where we cut, we are going to have different resolutions. For each of these different resolutions, we're going to construct knockoffs for the group of the variables, and then we're going to analyze the data using the lasso. The examples I'm going to show you comes from the UK Biobank, which I have already mentioned to you. In this data set, we are looking at about 600,000 SNPs, and we are only looking at a subset of the individuals, the unrelated British individuals, to avoid problems that are related to family relatedness and to different ethnic background. I have to say that actually the current version of this algorithm can deal both with family relationship and individuals of ethnic background, but I don't have results in good shape yet to share them with all of you. Here is a sense of what are these different resolutions that we construct, and we indicate them in terms of resolution as 100% means that you have one SNP per block, so you are actually using all the level of the resolution that you could get. This means that we're going to have 600,000 blocks, and the average block width in megabases is 0 because it's represented by one SNP only. Then you have these decreasing levels of resolution. The smallest resolution, the coarser resolutions that we get, it's 2%, which corresponds to an average block size of 50, an average block width of 0.2 megabases, and we have 12,000 blocks. Now, what you can see on this column is the average correlation between the knockoff and its original variable. And you can see exactly the phenomenon I've described for you, for which I said we're going to, instead of looking at single variables knockoff, we're going to construct this group. When we look at single variables, each variable is correlated to its knockoff with an average R-square of 0.7, which is quite high. Instead, when we look at this coarser resolution, the correlation between each variable and their knockoff, it's low and down to 0.2. This graph represents the same information, but instead of just giving you one R value, it gives you box plot for those. And these graphs simply observes that if we look at the correlations that we have to conserve to construct correct knockoff, we indeed conserve them. So if you look at the correlation between one variable and another one, and that variable and the knockoff of the other one, they are very much conserved. And here it's an one snapshot view of how this method works and what type of results it's going to provide. So this is again height, and it's we're looking at chromosome 12. At the very top here, you have the entire chromosome 12, and you have a representation of multiple lines that corresponds to the different resolution. At the bottom here, you have the coarser resolution, and you have a box drawn in correspondence of every group of SNP that has been selected as significant. And then as you increase, you are going to have boxes corresponding at a lower at a higher resolution, and so on and so forth. It's perhaps easier to look at this zoomed version of this central region here. Here you can count the different number of resolutions. They are indicated on the y-axis. So you can see here that we detect that there is something going on among these SNPs. This group of SNPs has something to tell me about height conditionally on all the other blocks across the genome. Then when I try to be a bit more specific and I say what among these SNPs is important, I can also reject this more specific hypothesis. It says this block of SNP has something to tell me about height conditionally on all blocks of comparable size across the genome. However, I am not able to make a more specific discovery that says exactly which SNPs in this block are important. In other positions, like in this one, I actually can make very, very specific discoveries and say this SNP here, this is actually only one variable, can tell you something about height conditionally on every other single SNP in the genome. And by contrast, this is the plot that I already shown you at the very beginning of this presentation. That is what you get from the analysis of this region from the standard univariate approach. You can see that while there is an attempt to interpret these p-values with these different colors block are not terribly interpretable, because if you actually look, they overlap. So we don't know what we're talking about, where is the signal, and we don't know how specific the signal can be. To bring this point maybe clearer, let's look at a simulation, so that where we know what the right answer is and we can compare how these two approaches fare. This is simulated data, and the phenotype depends truly on 5 different variants that are indicated by these little black lines at the bottom here. And in the univariate analysis, when the SNP it's really one of the SNP that is important for the phenotype, instead of having a black dot, this SNP is represented with a green asterisk. What's the difference between one column and the next one? It's the relative importance of these SNPs. So In this column, the heritability is small, so these SNPs are going to explain a smaller portion of the phenotypes, and in this other column, the heritability is stronger, so these SNPs are going to explain a bigger portion of the phenotype, or if you want, the effect size is larger. Now let's see what happens with the univariate models. Now the univariate models in both cases detect that there is something going on here, right? Because in both cases there are some SNPs that pass the significant threshold, so the geneticist would be alerted of the fact that there is something going on. Now, which of the two cases is better? When you have lower signal, you have a smaller number of SNPs that pass the threshold. This means that some of the true SNP do not pass it, but most of those that pass the thresholds are actually important. When you have stronger signal, which is arguably what you would want, the picture is much more muddled. Again, you have a sense that something is going on here, but you see that there is a larger number of gray dots that pass the threshold. In fact, the importance of the true SNPs as opposed to the not causal ones, those ones that are associated just because of linkage to disequilibrium, it's very difficult to discern here. If you look at what happens with the Knockoff Zooms, you have, in some sense, a similar, in some sense, a profoundly different picture. In both cases, at the low resolution, the methodology picks up that there is something going on. What's the difference between low signal versus high signal is that in the low signal case, the method cannot resolve very much among the 5 SNPs. In fact, it cannot resolve among the 5 SNPs at all. And we just know that in this portion of the genome that it's not very specific, there's something going on. When we increase signal, the method can resolve the importance of the different SNPs up to a very high resolution. In fact, here you can distinguish every single one of the 5 SNPs independently. So we have done a number of simulations and we are kind of running out of time, so I don't want to bother you very much. You can go and look on the published paper to get a sense of them. The simulations have done trying to be realistic, so we have used true genotypes and we have simulated phenotypes under a variety of scenarios, and we have compared our methodology with others. And what we see is that this is a list of the methodologies that we have used. What we see is that the methods that we have proposed always controls the false discovery proportion and has really power that it's comparable to other methods or better. But what we really shine on is that we can control the false discovery rate, which is not a trivial task, and we can localize precisely and informatively where the signal is. I want to show you just before finishing some of the results on real data. So again, we are in the UK Biobank, but at this level, instead of simulating phenotypes, we analyze true phenotypes. And I am presenting for you the results at low resolution compared to the results of a univariate method that is state of the art and whose results have been post-processes to be interpreted as independent loci in the genome so that they would be equivalent to these low resolution blocks. And what you have here is the number of findings. So you can see that our approach has a much larger number of findings than this competing one. A couple of slides on computational resources. Clearly doing this, it's not something that happens immediately, but in truth, the largest amount of time it's spent fitting these HMM models for our data, and these HMM models are actually fit on a regular basis for genetics data for a variety of other reasons. So you can imagine that this is cost that the analyst would bear in any case. Geneticists feed these HMM models to impute SNPs regularly to phase their data. So we don't really have to add a very serious computational burden on top of what is already done. So one way is looking at this context. This is fitting the HMM. It's where most of the time goes. Then you generate knockoffs, and then you have to do the analysis. Now, I said this is a time that the geneticist would spend anyway. Generate knockoff is what we need to do, and this is some serious time contribution, but not unbearable. You also have to keep in mind that for every new phenotype that you might want to analyze on the same cohort, you can reuse the same knockoffs. So this final mapping step can be really quite fast. Matteo Sesia has a very nice GitHub site where he presents, where he keeps the code and some simulation analysis and some markdown documents so that you can actually try out the method. And let me thank you for your attention, and thank you for putting up this conference in these strange times of pandemic. In the United States, where I find myself on top of the pandemic, we are also living very sad moments because of racism. So let me conclude with an invitation for everybody to do what we can to combat racism. Thank you very much.